Hi students, welcome to another classes. Today topic oxides of 16th group elements that are very important oxides in chemistry. So in 16th group elements form mostly dioxides and trioxides. Dioxides and trioxides. All elements form dioxides and trioxides. Some elements form the monoxides, sulfur, tellurium, polonium monoxides are very most stable. So here trioxides. So EO3 type trioxides, SO3, SeO3, TeO3, POO3. And sulfur also form heptoxide H2O7, that is the less stable, but sulfur form heptoxide also. So here dioxides and trioxides are very important in 16th group elements. Some properties about dioxides and trioxides. When compared to all dioxides, sulfur dioxides are more stable. Sulfur dioxides are more stable. When compared to all trioxides, sulfur trioxide is more stable. Sulfur trioxides are more stable. When compared to all oxides, sulfur oxides are more stable. These dioxides and trioxides are more stable. In particular, in dioxides, acidic nature top to bottom decreases, basic nature increases. And sulfur dioxide and selenium oxide are acidic oxides. These two are amphoteric oxides. Basic nature top to bottom increases. In this trioxides also acidic nature decreases, basic nature increases. Acidic nature decreases, basic nature increases. Basic nature is increases. When compared to dioxides and trioxides, trioxides are more acidic. When compared to dioxides, trioxides are more acidic. Dioxides are act as both acids and bases, both Lewis acids and Lewis bases. Why? Because they salt dioxides have vacant orbitals, accept the electron pairs. That's why Lewis acids extended to up to 6 coordinates number. So and also have lone pairs. These are have lone pairs. That's why these are Lewis bases. Here dioxides are act as both oxidizing and reducing agents. Reducing natures. But trioxides only act as oxidizing agent. These are only act as oxidizing power and oxidizing agents. So top to bottom, reducing power decreases, oxidizing power increases. Sulfur dioxide is a powerful reducing agent when compared to all dioxides and trioxides. So reducing power top to bottom decreases. Oxidizing power is increases. So tellurium oxide and polonium oxide are good oxidizing agents. In trioxides, all trioxides are oxidizing agents. Top to bottom oxidizing power increases. In acidic medium, SO3 is a good oxidizing agent due to protonation of the oxygens. The SO bond is easily break. That's why SO3 is a good oxidizing agent in acidic medium. So when compared to and trioxides are more oxidizing power. Dioxides are less oxidizing power. In oxidizing power top to bottom increases. Oxidizing power top to bottom increases. So dioxides are both Lewis acids and Lewis bases, and all trioxides are acidic nature. All trioxides are acidic nature, but top to bottom acidic nature is decreases, basic nature increases. So one by one. So monoxides. Except selenium, remaining elements can form monoxides. Monoxides. Except selenium, remaining oxides form monoxides. So here sulfur monoxide, sulfur dioxide react with excess of sulfur to form sulfur monoxide. Sulfur monoxide. So recently this is written as SO, but this is the wrong representation. This is the correct representation for sulfur monoxide. So here, this is the very less stable. The structure of the sulfur monoxide is SS double bond O. Here bond angle is 118. Bond angle is 118. Here 146 picometers. The bond length is 188 picometers. So single bond length is more than double bond. Single bond length is more than double bond. That is the very important stress. So remaining tellurium and polonium monoxides prepared from polonium SO3, POSO3. So to form POO plus SO2 and tellurium trioxide, sulfur trioxide, sulfonates, that means sulfonite, polonium sulfonite, tellurium sulfonite. To decomposes to form tellurium oxide plus SO2. So when compared to this all monoxide, sulfur monoxide is very less stable. Sulfur monoxide is very less stable. These oxides are formed in ground state. Ground state, sixth group valence is 2, combining capability is 2. So oxidation number may be plus 2 or less, minus 2 or sometime 0. In ground state, this group elements can form only 2 bonds. In ground state, only 2 bonds. For example, take the sulfur. So sulfur, so valence electron configuration is 3s2, 3p4. 3s2, 3p4. So here one pair is there, 2 single electrons are there. The 2 single electrons involved in bond formation. So these are monoxides. The monoxides. So these two are basic nature. This is the slightly acidic nature, almost neutral nature. So next go to dioxides. Dioxides are very important. Dioxides are more stable than when compared to trioxide for particular element. So SO2 is more stable than SO3, SiO2 is more stable than SiO3, SiO2 is more stable than SiO3, TiO2 is more stable than TiO3, POO2 is more stable than POO3. POO3 is very unstable compound, does not exist, very little won't exist. Here livermorium, we don't know the oxides of that elements. That is the radioactive element, newly discovered elements. So here dioxides. So SO2 is a gas. SO2 is a gas. SiO2 is a solid. TiO2 is a solid. POO2 is a solid. These two are ionic solids. And this is the more volatile solid. This is the more volatile solid. So in gas state, SO2 is a gas. SO2 is a gas. This reducing power top to bottom. What happens, students? Decreases. Oxidizing power is increases. When compared to SO2, SeO2 is a less reducing power, more oxidizing power. SO2 plus SeO2. SO2 plus SeO2, that is convert to SO3 plus Se. So here SeO2 is a good oxidizing agent. SeO2 is a good oxidizing agent. That is the very important in organic chemistry, students. So in SeO2 is a good oxidizing agent or selective oxidizing agent in organic chemistry. That is oxidize the allylic carbon, convert to alcohols in alkenes, and triple bonded carbon convert to oxides. So aldehydes and ketones. Terminal carbon convert to aldehyde, non-terminal carbon convert to ketones. And active methylene group in aldehydes and ketones, that is convert to terminal is aldehyde, non-terminal carbon is convert to ketones. So active methylene group convert to here oxidation is reacted. Aldehydes and ketones are formed. So these are very important oxidizing agent in organic chemistry. So in presence of SeO2, SO2 is easily oxidized. Here SO2 acts as reducing agent. Here SeO2 acts as oxidizing agent. When compared to SO2, SeO2 is a good oxidizing agent. SO2 is a good reducing agent. So SO2 reducing power is more in basic medium, less in acidic medium. That is a very important, students. So these two are dissolved in water. SO2 and SeO2 dissolve in water to form oxyacids, sulfurous acid, and SeO2 dissolve in water to form H2SeO3. Next, TeO2 and POO2 insoluble in water but soluble in concentrated acids and bases. That indicates dioxides of tellurium and polonium have amphoteric nature. Which nature, students? Amphoteric nature. So in gas state SO2 and SeO2 have linear structures. That is the very important, students. Linear structures. So structure of SO2, S double bond O, S double bond O is sulfur atom in first azido state. One lone pair is there, 4 single electrons are there, 4 electrons involved in bond formation to form 4 bonds. 2 are sigma bonds, 2 are pi bonds. 2 are sigma bonds, 2 are pi bonds. So 1 s orbital, 2 p orbitals involved in hybridization. 1 s orbital, 2 p orbitals involved in hybridization to form sp2 hybridization to form 3 sp2 orbitals. The 2 out of 3, 1 have lone pair, 1 orbital have lone pair. Remaining 2 orbital can form 2 sigma bonds with oxygen atom. So this sigma bond is sigma sp2p. So this sigma bond also sigma sp2p. Sigma sp2p, how many bonds are there? 2 bonds are there. So these pi bonds, one of the pi bond is here sulfur p orbital, oxygen p orbital. Sulfur have one p orbitals, oxygen also p orbitals. Here p pi bond, that is a p pi bond. Another pi bond is a sulfur d orbitals, sulfur d orbital. This is the 3d orbitals, 3p 3s, 3s. That is the very important. So one of the pi bond is d pi p pi bond. One of the pi bond is p pi d pi bond. So overall here sulfur dioxide have angular shape. This shape, students, angular shape. So selenium trioxide also in gas state, angular shapes. Which shape, students? Angular shape. 2 pi bonds. So here angle is approximately 119.5. 119.5. Bond length is 143 picometers approximately. So very important that bond angle. So due to lone pairs, lone pair and bond pair repulsions, bond angle is decreases. sp2 hybridization bond angle is 120. But due to lone pairs bond angle is decreases, but the bond angle not more decreases. Bond angle is more, not decreases, very less decreases. Why? Because here multiple bonds. Pi bonds repulsions are very more when compared to single bonds. That's why here, so bond angle is slightly decreases when compared to remaining. So sp2 bond angle is 120. So here lone pairs are there, bond angle is decreases, but the bond angle is very less decreases. The bond angle is very less decreases due to here bond pairs, more bonds are there, multiple bonds repulsions are more, that's why more like that. So slightly decreases, that is the very important, students. So here bond length is 161 picometers. Bond length is increases, bond angle is decreases. That value not known exactly, but when compared to here, their bond angle is less. So these are sulfur dioxide formed in first azide state. These all dioxides are formed in first azide states. In SO2 is a gas. In gas state, SO2 shape is angular. In SeO2 is more volatile solid. In this is also in gas state angular shape. So remaining are ionic solids. These are ionic solids, crystalline solids, So in solids, there are solids. So in solid state, SeO2 is a polymeric structure. Like that. SeO2 is a polymeric structure in solid state. That is a very important non-linear zigzag linear structure. Here OO bond is 125 angles and SOP here 98. How much? 98 plus or minus 2. So here 90. So these are very important, students. In O, S double bond O, SC double bond O, 90, here 98, here 25. That is the very important, students. So this bond length is more than this bond length. This bond length is more than Here double bond O length. This is the 178 like that. This is 173 picometers. Very less picometers. 173 and 173 and how much, students? 178. This bond length is more when compared to this bond length. In solid state, SiO2 is a non-angular, non-planar, that is a zigzag structure. So here polymeric structure. It is a polymeric structure. So all dioxides easily prepared but react with the elements react with oxygen. All dioxides are easily react. The elements react with elements combustion with oxygen to form SO2, and Se plus O2 form SeO2, and Te plus O2 form TO2. But sulfur also prepared from its ore minerals. FeS2 react with O2 to form Fe2O3 plus SO2, and zinc sulfide react with O2 to form zinc oxide plus SO2. But selenium and tellurium metals dissolve in concentrated acids HNO3s to form here tellurium easily formed H2TeO3 and 2TeO2 and HNO3. There water also there. After decomposition, after eating, the water and HNO3 evaporate to form TeO2. Here SeO2 is formed after evaporation. So when compared to all, here SO2 is a powerful reducing agent. SO2 is a powerful reducing agent. SO2 also act as bleaching agent. SO2 also act as bleaching agent. The bleaching action of SO2 is due to reduction. Bleaching action of SO2 is reduction. Bleaching action of SO2 is reduction. So here SO2 react with water in presence of water, moist condition, that is act as bleaching action to release the nascent hydrogen's final properties in H2SO4. Here color matters react with the hydrogen to form colorless matters. So bleaching action of SO2 due to reduction, remaining all bleaching action due to oxidation. For example, O3 is a bleaching agent, H2O2 is a bleaching agent, chlorine water is a bleaching agent. So bleaching powder also have bleaching action due to oxidation. So HOCl plus HCl, HOCl decomposes to HCl plus O, and H2O plus of O, O3, O2 plus O. This all are have bleaching action due to oxidation. SO2 bleaching action is due to reduction. The nascent hydrogens added to color matters to react with nascent hydrogen to form colorless matters. This is the some information about dioxides. So next go to trioxides. Trioxides are more important oxides in this lesson. So all trioxides are acidic nature. Top to bottom acidic nature is decreases, basic nature is increases. Here sulfur dioxide react with oxygen to form sulfur dioxide in presence of catalyst V2O5. So selenium react with O2 in presence of silent electric discharge to form SeO3. SeO3. But tellurium exerts telluric acid is 6 TeO6 decomposes to form tellurium oxide. Here selenium, tellurium, polonium. Polonium oxide is very less stable. Polonium oxide is very less stable when compared to remaining. So here all trioxides easily dissolve in water to form weak acids. H3H2SO4 and SeO3 dissolve in water to form H2SeO4 and TeO3 dissolve in water to form H6O6 telluric acid. So oxyacids of trioxides, these are anhydrides of weak acids. So acidic nature and stability top to bottom decreases. Stability and acidic nature decreases. Which is more acidic, students? H2SO4 is more acidic. Here very important factor. So in H2SO4, S double bond O, OH, less protonated oxygens. They are less protonated oxygen. Only 2 are protonated oxygens. In tellurium, 6 protonated oxygens are there. 6 protonated oxygens. Number of protonated oxygens increases, acidic nature decreases. Unprotonated oxygens have more inductive ability, accept the electron pair, so get a positive, easily lose H plus ions. Less unprotonated oxygens so more acidic, more stable. Top to bottom, acidic nature decreases due to protonated oxygens increases. So due to more protonated oxygens, acidic nature is less. And here solubility also decreases. TeO3 is less soluble in water due to less ability of formation of multiple bonds with oxygen. That is very important. So next, structures of trioxides. All trioxides in a trigonal planar shape is there, undergoes sp2 hybridization. So here very important, structure of the sulfur trioxide. In gas state, the structure is trigonal planar. Sulfur atom undergoes sp2 hybridization. Here bond angle is 120. Bond length in SO is approximately 143 picometers. So here sulfur forms 6 bonds in second azide state. In which azide state, students? Second azide state. So ground state electron configuration of sulfur 3s2, 3p, so here one pair is there, here one pair, 2 single electrons. Here how many bonds are there? 6 bonds. In ground state cannot form 6 bonds, only 2 bonds are formed. Next, first azide state. One pair is there. So one pair, one, four single electrons. How many single electrons, students? Four single electron can form four bonds. Here how many bonds are there? Six bonds. So first azide state also, so it cannot form trioxides. So second azide state. So six single electrons are there, six unpaired electrons are there. The six are involved in bond formation, six bonds are formed. So one s orbital, two p orbitals involved in bond formation to form sp2 hybridization. Involved in sp2 hybridization. One s orbital, two p orbitals involved in hybridization to form sp2 hybridization. Here three sp2 orbitals are formed. How many orbitals are formed, students? Three sp2 orbitals. The two are have single electrons that can form sigma bond with p orbitals of the oxygen atom. P orbital of the oxygen atom. P orbital of the oxygen atom. So which type of sigma bond, students? Sigma sp2p. sp2p. This is the sigma sp2p. Sigma sp2p. How many bonds are there? The type of bonds? Three bonds are there. So in sulfur, a residue state in pure orbitals contain three pure orbitals. The three pure orbitals can form pi bonds. The three pure orbitals form pi bonds. So one of the orbital is p orbitals, another two orbitals are d orbitals. Here p orbital is there. So sulfur p orbital form one pi bond. Here d orbitals. So oxygen p orbitals form one pi bond. So here sulfur d orbitals, oxygen p orbitals can form one pi bond. So how many pi bonds are there? Three pi bonds. One of the pi bond is p pi bond. So another pi bond is d pi p pi bond. So this is also d pi p. So that is the very important. So these are structure of the sulfur trioxide. Sulfur trioxide in gas state. In solid state, sulfur trioxide exists in three different forms. Three or more than three different forms. So alpha, beta, gamma. Alpha, beta, gamma. So alpha, beta, gamma forms. So gamma form is a cyclic trimer and tetramer. Cyclic, mostly cyclic trimer. So S3O9. So what is the structure? Sulfur trioxide. So this is the trimer form of gamma form, cyclic trimer. So here very important, how many SOS bonds are there? Three SOS bonds. How many S double bond O's are there? Six. How many sigma bonds are there? How many pi bonds are there? How many pi bonds are there, students? 6 pi bonds. How many sigma bonds? You have to count it. How many sigma bonds are there? How many sigma bonds are there, students? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sigma bonds are there. Total number of bonds. So next, in beta form is a cyclic form. Here bond angle is here approximately a bond length 161 162 approximately picometers. So here approximately 143 picometers. So beta form, that is the polymeric form, S double bond O, O and O. So like tetramer, like that. But alpha form is a cross-linked polymer, that is the most stable. Alpha form is a most stable, that is the very, very important students. In solid state, SiO3 exists as tetramer, SiO4 and 12. In solid state, SiO3 exists as tetramer, cyclic tetramer. This is the very, very important stress. So here very, very important points. Dioxides are more stable than trioxide of the particular elements. So sulfur trioxide and dioxides are more stable, more acidic. So sulfur dioxide is a good reducing agent. Here dioxides act as Lewis acids and Lewis bases. All dioxides are both oxidizing and reducing nature. Reducing nature top to bottom decreases, oxidizing power increases. So these are key points, students. When compared to dioxide, trioxides are more acidic. These oxides are very, very important, students. Thank you very much, students.